Hello, Tanya Laird here, and welcome to part 2 of lecture 17 of ENGR 2301 Engineering Statics. In this portion of the lecture, I want to work through some basic examples applying the parallel axis theorem to adjust, moments of inertia for rigid bodies, or for cross sections, I should probably say, from one axis to a parallel one. And this is a follow-up to part 1 of this lecture, which is previous to this on the playlist. Okay, so parallel axis theorem examples. I'm going to work through two different examples. And the first one is going to be more of a formula-based one, where I show just how to apply the parallel axis theorem at a basic level. And we're going to first consider this. And what I want to do is as follows. Maybe I could call this example 1. So I'm going to have a circle, a circular cross-section, or just a circle, positioned at some point on the y-axis. And this thing is going to have a radius of r, and the center of the circle is going to be located some distance h above the x-axis, like so. Some distance h above the x-axis. So this is given. And I want to find the formula, the formula for the ix prime, or for the moment of inertia with respect to the x-axis for this circle. Moment of inertia with respect to the x-axis in terms of r and h. In terms of r and h. Those are the two defining geometric characteristics of the system. Again, we're looking at this circular area here, and I'm trying to find the moment of inertia of this thing with respect to the x-axis. So if we remember from part 1, the main theorem, or the main formula that we're going to use, solution here, the main formula we're going to use is ix prime is equal to ix plus ad squared. Plus ad squared. And remember, ix, as we defined it, is the moment of inertia about a centroidal axis, again going through the centroid. A centroidal axis, and A is the area, and the D, the lowercase d is the distance between the parallel axes. Between the two parallel axes. Okay, so let's go ahead and do that. Now the first step is getting ix. This is the moment of inertia of the circle about its own centroidal axis. Of the circle through a horizontal axis passing through the centroid. Or about a horizontal axis, or just about an x-axis, positioned through the centroid. Through the centroid. So basically, I'm going to look at it as if I had an x-axis up here. I'm going to calculate the moment of inertia of this thing with an axis passing through the circle, through the center of the circle. Now, so let's consider this for a moment. Let's look at this. So now I have a different ix, or a different x-axis, x and y. I have now positioned an x-axis going right through the center of the circle. Maybe I can make something a little circular for a circle. There, a lovely drawn, perfect circle. Man, I gotta practice my circle drawing. Close enough. Okay, and this thing has an equation r. Now, to make the math a little bit easier, what I'm going to do is I am going to work through this using only the first quadrant. Basically, the I of quadrant 1, because this thing is symmetric about the origin, or because it's symmetric about both the x and the y-axis, I can basically calculate the I, or maybe I can say the Ix total will be equal to the Ix in quadrant 1. And you can do this for any shape that is doubly symmetric and is positioned at the origin, or you're taking the moment of inertia about an axis passing through the origin. So, well, it's not equal to this; it is equal to 4 times this, and this makes intuitive sense. I can calculate just the moment of inertia of only this piece here, and then work through the integration, and then just go and multiply the final result by 4. So that's what I'm going to do. So let's look at this then. We have this part of the circle, it's in the first quadrant, and I want to find the moment of inertia of it. So we have this here. And because we have the formula Ix, well, we do have the formula Ix equals the integral of y squared dA. Now, we saw in lecture 16 that we can go and, when doing the Ix, do a transformation to use a vertical element of integration, but because circles are fairly similar equations either way, it's not really going to help us much to switch it to a horizontal area of differentiation, a vertical differential element rather than a horizontal differential element. So I'm just going to leave this in the standard horizontal differential element. So I'm going to use a differential element like this. This can be my differential element. And the equation here, well, I know this thing has radius r, and I also know the equation of a circle is x squared plus y squared equals r squared. So the equation of this line, solving for x, not y, again, because we're doing this with the horizontal differential element, we have a dy, so therefore everything needs to be in terms of y. So I need to solve this for x, and that comes to x equals the square root of r squared minus x squared. R squared minus x squared. So our equation is going to be x equals r squared minus x squared, and then our dA, again, this thing's going to have a width of square root of r squared minus x squared, and it will have a height of dy. So therefore, dA is equal to the root of r squared minus x squared times dy. Oh, oops, I have x twice there. R squared minus y squared. There we go. One of those things. Square root of r squared minus y squared, and then a dy here. So then we can set up our integral, and Ix then is going to be equal to the integral from 0 to r. We would be integrating in the y from 0 to r times y squared dA, and this is then going to be equal to the integral, or just substituting in our dA term that we'd already developed, of integral from 0 to r y squared times dA, which again is square root of r squared minus y squared, times dy. Now, on some of these, when I've been working through these integrations, I've just told you, oh, it's a simple integral. It's just a basic polynomial integral. It's not that bad. This is actually a tricky integral, so I think I actually will go ahead and work all the way through this one. So this is one of those integrals that's actually best solved by applying trigonometric methods. So stand back, we're going to try some fancy integration. I'm going to do not a simple u to u substitution, but I'm going to instead do a trigonometric form conversion. So what I'm going to say is, look, I know that y is equal to r sine theta. I'm going to say let y equals r sine theta, and that is true in most cases. So I'm going to say, or actually it's true in all of this, for all cases here in this problem. So I'm going to let y equals r sine theta, and then that means dy. Basically what I'm doing here is I'm converting this to a polar form. Dy is equal to r cosine theta d theta. And then, again, if I just take the derivative of this, I will get that dy is equal to r cosine of theta d theta. And then the bounds on this thing, instead of going from 0 to r, we're going to go from basically our bounds, instead of from 0 to r, we'll go from, if we're doing this in terms of thetas, it will go from 0 to pi over 2. The integral from 0 to pi over 2. So we have this now, and so let's go ahead and work through this. And this is going to take a bit of time. There's quite a few steps in this. If you don't want to see me work through a very long integral, feel free to fast forward at this point. You could also throw this into an algebraic solving system or something like that, but I was feeling a little bit mercurial today and wanted to work through a long integral, so I don't do enough of those in this class. So let's put in the y here, and I have the integral of y squared, which is the integral, and I'm just going to do it in the indefinite form rather than the definite form right now. So I'm just going to ignore the bounds, and then I have quite a few steps. I mean, there's going to be a lot of lines of integration here. It's a fairly complex one, so I'm going to go and ignore the bounds for now, and then I'll put those back in at the end. So instead of having y squared, we are going to have our r sine theta quantity squared times the square root of, well, r squared minus r squared sine theta. Here, what I did was I simply, for this one here, I replaced y with r sine theta, and so we'd have r squared theta sine squared theta. And then r dy is equal to r cosine theta d theta. So outside the root, we have r cosine theta d theta. Now, at first glance, it seems like we're not making any progress at all. I mean, it looks like I've actually made this thing even more complex, but bear with me, we will get through this. So next, I'm going to go ahead and expand this out, and I might go ahead and factor this. So I'm going to have the integral of, let's see, that's going to be r squared sine squared theta, r squared sine squared theta, times the square root of r squared times 1 minus sine squared theta. And again times r cosine theta d theta on the outside of the root. R cosine theta d theta. And so we have that, and I'll close parentheses there. Then I'm going to pull out this r squared, and I'm going to recognize a trig identity here. And this trig identity, of course, is the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. Cosine squared theta plus cosine squared theta plus sine squared theta is equal to 1. Therefore, 1 minus sine squared theta is just cosine squared theta. So this is then the integral of r squared times sine squared theta times r. I'm pulling the squared r square root out times cosine squared theta. Times cosine squared theta, and then times another r, or the same r, cosine theta d theta. Cosine theta d theta. Then I can go and say, okay, well, let's think about this. What do I have? I have the integral of, I have 4 r's here, r squared, r, and r, so I can just combine those together into a single r to the 4th. And then I would have, okay, well, I would still have that sine squared theta from here, sine squared theta, and then I can also say that I have if I take the square root of cosine squared, I have a single cosine times another cosine, which would give me cosine squared theta d theta. Isn't this lovely? And so then what I can do is I can pull out this r to the 4th. So I then have r to the 4th. And the reason I can do that is because, notice, this is an integration in terms of theta, and so r is a constant of integration in this context. And so then this would be r to the 4th times the integral of sine squared theta cosine squared theta d theta. And looking at this just reeks of half identities and double angle identities and all that kind of stuff. So I'm going to first recognize here that this is equal to r to the 4th, that's not changing, but times the integral. This is basically sine theta times, well, okay, I'm going to do this, actually let me do this on the next slide here. So I'm just going to take this, and I got to do a few fancy steps. So I'm going to do this on the next slide, copying this line here, the r to the fourth. So I have r to the fourth times the integral of sine squared theta cosine squared theta d theta. Sine squared theta times cosine squared theta d theta. Now, what I would like to do is I would like to put in a 4 in here, and you'll see why in a second. R to the fourth over 4, and what that would allow me to do is to say, okay, well, basically I have 2 sines here and 2 cosines here. So if I put the over 4 there, I can write this as 2 cosine theta sine theta times 2 cosine theta sine theta, and then times d theta, and then times d theta, of course. That's not changing. So again, I have 2 sines and 2 cosines, and it behooves me to have this 2 in here, as we'll see. And the reason I'm going to be able to do that is because there is a formula, the double angle identity, one of the double angle identity formulas, that says that the sine of 2 theta, this is a trig identity, the sine of 2 theta is equal to 2 cosine of theta sine theta. And that's why I'm putting this into this form, because then what I can do is I can write this as r to the fourth over 4 times the integral of sine of 2 theta times the sine of 2 theta, and then times d theta. Or I can say this is r to the fourth over 4 times the integral of sine squared of 2 theta. Sine squared of 2 theta d theta. So we are getting somewhere, theoretically. Let's see, so we have that, and then we can apply a different formula that says another trig identity that says basically that 1 minus the cosine of 2 theta over 2 is sine squared theta. Now we already have a 2 theta, so we'll have to double that again, and we'll end up with a 4. And so we'll have the same r to the fourth over 4 times the integral of 1 minus cosine 4 theta divided by 2 d theta. Again, I had to double the theta when I went from the sine squared to the cosine d theta. And so I'm going to go ahead and separate this out at this point. Well, first I'm going to pull out the half, the 1/2, so that'll become an 1/8 on the outside. I'm going to break this into 2 integrals. This will be r to the fourth over 8 times the integral of basically 1 d theta. Although you really wouldn't have to do that at this point. I just wanted to do this. That made a little more sense when I was working through it. Then we'll have r to the fourth over 8 times the integral of cosine of 4 theta d theta. D theta. Now we could do this. We could handle this. Well, this one's easy enough. This one here, the integral of 1 d theta is just going to be theta. So we end up with r to the fourth theta divided by 8, r to the fourth theta over 8, and then here, well, I can think of this as I know that this is basically going to be the derivative of this here. The cosine 4 theta is the derivative of sine 4 theta, and we just need to add a 1 over 4 on the outside to balance that out. So this is then minus r to the fourth over 32 sine of 4 theta. If you're having trouble envisioning that, just imagine taking the derivative of this. So now we just need to go and apply our bounds. So I'm going to bring this back, and we would have the bounds, the integral from 0 to, well, we already got rid of the integral sign, so instead I'll just write this as r to the fourth over 8 times theta minus r to the fourth over 32 times the sine of 4 theta. And this evaluated from 0 to pi over 2. This evaluated from 0 to pi over 2. Then, if I want to just do some substitution here, I'll do the pi over 2 case minus the 0 case. First of all, I'll have, let's see here, r to the fourth over 8 times pi over 2 minus r to the fourth over 32. Now, this is interesting. The sine of pi over 2. or the sine of 4 times pi over 2, well, if you think about our unit circle, 0 is here, pi over 2 is here, and 4 times pi over 2 is all the way back to here, which is 0. So that's basically asking the sine of 0. The sine, or I could think of it as the sine of 2 pi, which is the sine of 0, and that, of course, is 0. Then, well, let's see here. If I put in 0 for this, well, this was r to the 4th divided by 8 times 0, so that, of course, is 0. Sine of 0 is 0. And then r to the 4th over 32 times the sine of 4 times 0, which should of course surprise no one to be that this is equal to 0. This whole thing is equal to 0. So really all of these terms, actually that should be written over here a little bit more. Sine of 2 pi, which of course makes this whole thing equal to 0 there. And so we are just left with nothing more than r to the 4th, pi r to the 4th, over 32. Or sorry, over 16 here. Pi r to the 4th over 16. Now we just have one other step to do, and that is to go back and realize that we're working with only 1/4 of the circle. Well, one quarter of, or one thing left on this step anyway. Again, this is 1/4 of the circle. This is the ix of 1/4 of the circle. So what I'm going to do instead, or what I'm going to do next is, I'm going to say, look, again, for something that is doubly symmetric and we're taking the moment of inertia about the origin or about the centroid of it, all I have to do is just multiply by 4. So the actual ix is 4 times pi r to the 4th divided by 16, and that produces a value of just pi r to the 4th over 4, which is what you'll find in any moment of inertia formula in any textbook, on Wikipedia, or wherever you might be looking. Now, unfortunately, we're not done yet, but actually we are almost done, because the final step, the only one that actually involves the parallel axis theorem, is rather simple for this particular problem. The second example will involve a bit more work. But here, again, we have our circle, and we have calculated the moment of inertia about ix, or about x. And really, when I said the original problem said calculate about the x-axis, but in the context of moments of inertia, this is basically my ix prime, and we have this distance h here. So I know ix is equal to, again, pi r to the 4th over 4. Pi r to the 4th over 4. And I also know that ix prime, the shifted moment of inertia, will be equal to ix plus ad squared. Plus ad squared. And this is actually fairly straightforward. This is pi r to the 4th over 4, and then plus a. Well, I know this isn't complicated at all. I definitely don't need to do an integral for this part. The area of the circle, of course, is nothing more than pi r squared. And then I have my h, and that's just h squared. And really, that's it. So yes, most of this problem was actually applying, calculating the integral of the moment of, going through the integral and calculating the moment of inertia of the circle itself. Once you actually have that, I do like this because this really does illustrate the power of the parallel axis theorem. See, think about this. And that's really why I wanted to work through this example. Is that, imagine if I wanted to just calculate the moment of inertia of this thing without doing the parallel axis theorem. How would I do that? Well, that would be a bit tricky. What I would really have to do is, if I wanted to do this without the parallel axis theorem, I would have to work through an integral that is essentially just as I would have to work through, backing up, I would have to work through an integral that is just as complex as this one, but I would have to do it twice. Because what I would have to do is, and even worse actually, I would have to do something like this. I would probably, if I wanted to do, well, how could I do this? I'd probably do it just like this. If you were to do this without the parallel axis theorem, I would almost look at this like this. I would calculate, if I would look at this half of the circle, and let's see, I would first calculate the area of maybe the region in blue here that I'm going to derive. Well, not calculate the area, sorry, calculate the moment of inertia by integration of this region in blue here. Then I would also calculate the moment of inertia in the area in purple here, basically below the lower boundary of the circle. And then I would basically, to get the combined, or the moment of inertia of just the circle, I would take the one from the top boundary of the circle all the way down to the axis and subtract the moment of inertia from the shape basically below the bottom boundary of the circle. And that would give me the moment of inertia, the subtracted moment of inertia, or just the moment of inertia of this of half the circle, and then I would double it to get the other half. Again, assuming you are doing this in rectangular coordinates. There are ways, of course, to do this with just by default with polar coordinates, but those have their own challenges at times. All right, so I think I'm going to stop here in this video. In the next video, I think I'll throw in another portion of this lecture that I do want to include a more tabular form of calculating moments of inertia for compound shapes that I think that would work as a standalone video. So I think that'll do it for now. Please let me know if you have any questions. This is part 2 of lecture 17 of ENGR 231 Engineering Statics. Tanya Laird here. And again, if you have any questions, feel free to let me know. Hope you found this enjoyable. Well, enjoyable probably not with that extremely long form of integration, but at least I hope you've learned something or found this, if nothing else, bearable. So again, please let me know if you have any questions. If not, I'll see you soon for part 3 of lecture 17. And as always, thank you.